What's up, everybody? It's Miss Brothers. So this is one of the practices that we're doing. This is page 1 of the practice on thermal energy and specific heat. So if you look at the instructions at the top, it says you're going to use the equation Q equals mc delta T to answer the following questions and use the table for specific heat values as needed. So this table comes in really handy for this page because it has different substances and it has their specific heat. So we have essentially 8 different substances here. In this column we have water, iron, copper, and aluminum and their specific heats. In the third column we have silver, sand, lead, and carbon and their specific heats. Okay, so we're going to be using these specific heats as we go through these problems. All right, so let's go ahead and let's do all 5 of these, and we'll try to get through these without too much trouble. And again, I'm going to be working with that process that I think is really important when it comes to doing these problems. And process becomes our little go-to. And again, if you want to, it's important that you come up with your own process. But I really have a process that I like to use, and again, if you want to know the steps of that process, then you're going to look in the Unit 2 Daily Notebook, and you're going to look on slide 35 for that process, okay? So, and one of the things you have to remember is that your teachers are often going to ask you to do this. They're going to ask you to show your work, and if you're going through this process and writing down the steps of the process, then you're doing that. Then you're showing your work, okay? So let's do the first one together, and let's walk through that process. And again, I'm going to show you some of the things that I do to kind of help me along as I'm trying to work through these problems. So it says, find the change in thermal energy when 640-gram piece of copper cools from 375 degrees Celsius to 26 degrees Celsius. And again, you guys, step 1 of the process is always the same. What am I trying to figure out? What am I trying to solve for? And so we're looking for context words like what or how or why or find. These are all words that we use to kind of signal to us that what is it we are looking for. So in this case it says find the change in thermal energy. So we're trying to find thermal energy. And if you remember, ladies and gentlemen, that when it comes to these symbols, we have to make sure we know what these symbols mean. What is Q? What is M? What is delta T? And just remember that Q equals energy, M equals mass, and I'm just going to write this down because I feel like we can't write this down enough. That C, or in my case, CP, is specific heat. And finally, that delta T is our change in temp. That's probably kind of hard to see, but hopefully you can see it well enough. And again, that's part of what I gave you in those 14 things that we need to remember about thermal energy and specific heat. We have those. We're going to keep going over and over those. If you remember nothing else about this process, remember those things. So now what we have to do is we have to set up our formula. And again, if you can't remember the formula Q, then you can use your triangle. And again, we use the triangle by covering up whatever it is that we don't know. And in this case, we don't know the change in thermal energy. So we cover up the Q and we use everything that's left. In this case, we're using our mass times our change in temperature times our specific heat, or M times delta T times CP. So let's see what we have so far. Do we have enough energy? Do we have enough information to fill this formula? Q equals mass times change in temperature times specific heat. Well, let's figure it out. Do we have our mass? There it is, 640 grams. We know that's the mass because it has the unit G for grams. Do we know the change in temperature? We don't, not yet, but we do have our starting or initial temperature right here, and we have our final temperature or our 2 temperature right there. Do we have our specific heat? Well, it doesn't say anything in the problem about specific heat. However, it does tell us that we are dealing with copper. So that means I need to go up into my chart here. I need to find copper. There it is. And that tells me that I have a specific heat of 0.385 joules over grams, excuse me, degrees Celsius. So I almost have what I need to get this problem going. But first, I have to find that delta T. And I do that by using the formula TF minus TI, or final temperature minus initial temperature. So my delta T is going to be equal to my final temperature being 26 degrees Celsius minus my initial temperature, 375 degrees Celsius. So now what I know is that my change in T is going to be equal to 26 minus 375 equals a negative 349 degrees Celsius. Okay? Now, this negative, you guys, becomes extremely important. Okay? So don't just ignore the negative sign. And what this means is this, you guys. It means that my piece of copper cooled from 375 degrees. It lost 349 degrees and ended up as 26 degrees. So this is, by saying negative 349, I'm showing that my that my copper lost energy or cooled. But now the good news is this: we have all of the information we need to solve for Q. So when I do that, Q is going to be equal to my mass, which is 640 grams, times my change in temperature, which is a negative 349 degrees Celsius, times my specific heat, which for copper is 0.385 joules over grams degrees Celsius. So now what we can do is we can calculate for Q, and we know that our final unit is going to be joules because the unit for thermal energy is joules. So let's go ahead and do that math. 640 times negative 349 times 0.385 equals, so my energy, my Q equals negative 85,993.6 joules. And again, you guys, the most important thing to remember is that I have to remember to include that negative sign. And that tells me that I've had a thermal energy change that caused, or a loss in thermal energy that caused this copper to cool from 375 degrees Celsius down to 26 degrees Celsius. So that leads us to question 2. It says, in question 1, is thermal energy gained or lost? And how do you know? Well, we know in a couple of ways. One, we know that it has been lost. We can just say that. And we know that for 2 reasons. One, we have a negative thermal energy number. And in this case, it was minus 85,993.6 joules. And the other reason we know is because it says right here in our problem that the copper cooled. And when something cools, if something cools, it means that energy is going out of our system, and as a result of that, we feel that as something that's being, this will eventually cool. We feel the energy coming out of it. Okay, so if we were talking about endothermic or exothermic, we could actually say that this is exothermic. And again, if you remember the conversation we had about endothermic and exothermic processes, when there's energy leaving our system, we would say that that is exothermic. It is exiting our system, and therefore it's exothermic. Okay? Fun. Yay! Applying all these ideas together at once. Neat. All right, let's do problem 3. What we want to know is how many joules, and let's go ahead and put a square about that because that's our how, of heat are required to raise the temperature of 555 grams of water from 12.6 degrees Celsius to 18.7 degrees Celsius. So right off the bat, we know we're trying to find energy. We're trying to find our Q again. So let's go ahead and see what we have here. So again, if we go to our triangle, we know that Q is the same as saying, for looking for Q, it's mass times change in temperature times specific heat. So M times delta T times C, or CP in this case. So let's go ahead and write that down, because remember, I think it's really important to write our formula every time we do one of these problems. So it's going to be Q equals mass times delta T times specific heat. So let's go through and figure out what we have right now and what we still need to get. Do we have our mass? Yep, there it is right there, 555 grams. Do we have our delta T? We don't, but we do have the data that we need to calculate delta T. And do we have our specific heat? Well, we don't have it in the problem, but we've been told that this is water. And if we look at our table up here, we know that water has a specific heat of 4.18 joules over grams degrees Celsius. So the next step is we have to find our delta T. So we can't go any further with this problem until we know our delta T. And again, delta T is TF minus TI. And again, you don't necessarily have to write this formula. I'm doing it so that you'll remember the process. So delta T equals, we started at 12.6 degrees Celsius. That's our initial temperature. And then our final temperature was 18.7 degrees. So our TF is right here, 18.7 degrees Celsius, minus my initial temperature, 12.6 degrees Celsius. So that's going to leave me a change in temp, 18.7 minus 12.6. That's going to be 6.1 degrees Celsius. That's my delta T. So now I have everything I need to start working through this formula. So Q equals my mass of 555 grams times my change in temperature, 6.1 degrees Celsius, times my specific heat of water is 4.18 joules over gram degrees Celsius. So once I do that, I'll have my Q. So let's go ahead and do that. 555 times 6.1 times 4.18 equals 14,151.39. And because we are dealing with energy, this is going to be joules. And I can also go through and cancel my units algebraically. And I'm going to go ahead and circle that answer. Okay, and again, we just went through that process from start to finish. Let's do the next one together. And again, you guys, if you have a good handle on this, if you feel like you can do number 4 and 5 on your own, you can just stop this video. You can stop watching it and go do whatever. But if you're still, excuse me, struggling a little bit and you want a little bit of guidance, you can keep watching. Or what you can do is you can shut this video off. You can try to do number 4 on your own and then do it and then come back and watch, turn this back on and watch me do number 4 and be like, yeah, I got this nailed. So you can use these videos any way you want. You don't have to sit here and just watch the whole video, okay? So let's go through number 4. It says a 4,375 gram iron sculpture sat in the sun all day. Let's go ahead and underline that because that's important information. That's the mass. During that time, its temperature increased to 45 degrees Celsius. That seems important. I'm going to underline that. An hour after the sun had set, the temperature of the sculpture is 29.4 degrees Celsius. So how much thermal energy was lost by the sculpture? Okay. Well, what we're going to do here is we're going to do a little bit of, this one is easier than you think it is, because all we're really doing is we are setting some things up to figure out this. We've got all kinds of information in here, so let's figure out what we've got. So we're trying to figure out how much thermal energy was lost. And I'll ask you right now, do you think this is going to be a positive or a negative answer? That's all I'm going to say. Okay. So there's some information that we need to figure out. We have the mass. We know this is iron. This is going to be important. We've got to figure out how much thermal energy. Thermal energy, you guys, is Q, remember. So we know we have to solve for Q. Let's go back. And let's cover up Q because we don't know Q. It's going to be mass times change in temperature times specific heat. Well, what do we have? Do we have the mass? Yes, we do. There it is, 4,375 grams. Because our mass times our change in temperature times our specific heat. Do we have the specific heat? We do, because remember, this tells us that we have iron. And according to our table up here, iron has a specific heat of 0.449 joules degrees Celsius. Do we have our change in temperature? During that time, its temperature increased to 45. After an hour, the sun had set, and the temperature of the sculpture is 29. So we have our initial temperature at 45, and then the sun set and it cooled to 29.4. So let's go ahead and calculate for our change in temperature. TF minus TI. So our change in temperature, we started at 45 degrees. We finished at 29.4. So our TF is going to be 29.4 degrees Celsius minus 45 degrees Celsius because our initial temperature was 45 degrees. So our change in T equals, let's go ahead and do that, 29.4 minus 45. That is negative 15.6 degrees Celsius. So now we have enough information, we can solve for Q. So Q equals mass, which is 4,375 grams, times my change in temperature, which is negative 15.6 degrees Celsius, times the specific heat of iron, which is 0.449 joules over grams degrees Celsius. Again, I got that number from up here. There's iron right there. So my Q equals, I'm going to do the math, 4,375 times negative 15.6 times 0.449 equals negative 30,644.25. And again, you guys, because this is Q and we can cancel out grams and we can cancel out degrees Celsius, that leaves us with joules. So the question was how much thermal energy was lost. 30,000 plus joules of energy was lost, and we know it was lost because our Q ends up being a negative number, and it's a negative number because we cooled from 45 degrees Celsius, which is pretty warm, down to 29.4 degrees Celsius. Okay. All right, let's do this last one. Now, for this one, it's saying a metal cube containing 15,750 joules of energy is placed into water. After 5 minutes, the cube is removed and now contains 3,575 joules of energy. So how much energy did the water gain? Now, one of the things you have to remember about this problem is that energy is never created or destroyed. It's transferred. And so what you have to remember about energy is that somebody else's energy loss, somebody's energy loss, or something's energy loss is somebody else's energy gain. So let's figure out. So we have a metal cube, and it starts with 15,750 joules of energy. And after 5 minutes, the cube is placed in water. After 5 minutes, the cube is removed, and now it has 3,575 joules of energy. So 3,575 joules. So what we're trying to figure out is how much energy did the metal cube lose when it was placed in water. Well, let's do the math on that. 15,750 minus 3,575 equals 12,175. So that's how much energy was lost, and again, that's joules. That's how much energy was lost by the metal cube. Now, the question is, how much energy did the water gain? Well, if the cube lost this much energy and it was sitting in the water, guess how much energy the water gained? It gained 12,175 joules. So this is not trying to trick you. It's just helping you understand and realize that if one substance loses energy, that energy has to go somewhere. And if you draw the picture, so here's a picture of a beaker with some water in it, and here's a cube that has X amount of energy. So you have all of this energy that leaves. Where does it go? That energy goes into the water. So that's one of the things you have to realize is that energy isn't being created or destroyed. That energy is simply being lost by one system, in this case the metal cube, and it's moving into another system, in this case the water. So that's what you're trying to remember. This one is not as tricky or as difficult as you think it is. It's just whatever the cube loses, the water gains. Ta-da! All right, guys. If you have any questions about how I went through this, or if you have any questions about number 5, just let me know. But that one, this is pretty much one of the big laws of thermodynamics right here, is that when it comes to energy, it's always transferred. It's never lost or destroyed. It just goes. It's lost, but the energy is not lost. It just goes into a different system. Okay. Hopefully that wasn't too confusing. Right on.